Welcome to Lab 3 for Physics 2. The purpose of this lab was to observe how resistors, capacitors, and batteries interact with each other in a circuit. To predict the quantities related to the circuit analysis was used. The ammeters and voltmeters were used to measure these values and compare the real-world results to the prediction. So the results were that the change in potential across a complete circuit will always sum to zero, and increasing the resistance in an RC circuit increases charging and discharging time of the capacitor. So some physics principles: Kirchhoff's circuit law, two parts, which is the loop rule, which is the sum of all potential differences around the loop is zero, and the node rule, at a node, the sum of currents flowing into the node equals the sum of the currents flowing out of the node. And then Ohm's law, which is voltage equals current times resistance, V equals IR. So, measuring current, and there's a picture on the right of our in-lab setup. Using Ohm's law, we found that the ammeter measured it was 0.2, but then with our math, it was 0.03, and we used bulbs instead of actual measured resistors because our TA told us to. Then for the voltmeter, we did this one online in the series. You can see the picture there. The voltmeter has a very high resistance, so that allows a very little current to flow through the ammeter, making the reading zero. But in parallel, the current is still able to flow through the circuit, so it has an uninterrupted reading on the ammeter, and there's a voltage drop along the component on the voltmeter. So the voltage around the circuit, as you can see on the right top, there's the labeled A, B, C, D, E, F, G, and H, and that corresponds to the voltages on the left there. And you can see that they should all sum to zero at the end, and then there's a graph on the bottom right for a visualization of this. Then an ammeter in parallel. So putting the ammeter parallel to one of the resistors, that introduces a new loop for current to flow in. And this loop only includes one of the two resistors, which increases the current, and you can see the math down there. I equals the change in V over R, that equals 0.06, which is what is showing on the ammeter. And as you can see in the top right picture of the online version, a new loop is opened once you add the ammeter in parallel. So here's our videos of charging and discharging a capacitor. For charging.
Oh, wow. And it is faded floating. Just like.
And discharging.
And when the capacitor is charging, it is faded.
I see.
Okay. So when this one is fully charged, so it.
And so all in all, it took 9 seconds to charge the capacitor and 9 seconds to discharge it. And in the discharging, the light went out and it discharged the capacitor. Here is the analysis, and here's a graph of the time dependence of a discharging capacitor using our values. And the initial voltage is 3 volts, the resistance is 1.7 ohms, and the capacitance is 1 F. And our 9-second charge and discharge times seems on par with this graph, if not a little long, so there could be some sources of error. The sources of error could have been errors in the timing or an incorrect capacitance value. So the discussion questions. What if you charge a capacitor with no resistor in the circuit? How quickly would our ideal model predict the capacitor to reach full charge? And you can read the rest. So my answers were, in an ideal model, the capacitor charges instantly because the sum of the voltages around the circuit is zero. To satisfy V equals IR, when resistance is zero, the current must be infinitesimally large. That would instantly charge the capacitor in a perfect world until charge voltage Q over C is equal to the battery. But in reality, that doesn't happen, and it doesn't charge instantly. There is no material that could have a perfectly zero resistance value. The wires that connect them have a low resistance value. It's low, but it's not zero. And that is why the capacitor will charge quickly, but not totally instantly.